Now we're going to define what an exact equation is. But first, we need to understand what a total differential is. The total differential of a function f of xy is defined to be df equals the partial of f with respect to x times the differential dx plus the partial of f with respect to y times the differential dy. This should be familiar from Calculus 3 when you learned how to linearize functions of two variables. Let's look at an example. Let's find the total differential of f of xy equals sine of x times cosine of y. Finding the total differential is as simple as calculating the first partial derivatives of f and plugging them into the formula for df. The partial derivative of f with respect to x is going to be the partial derivative with respect to x of sine of x times cosine of y, which is cosine of x times cosine of y, since we treat y as a constant and just differentiate with respect to x. The partial of f with respect to y is the partial with respect to y of sine of x times cosine of x. So now we're treating x as a constant and differentiating with respect to y. So our sine x stays as sine x, and the derivative of cosine of y is negative sine of y. So that becomes negative sine of x times sine of y. So using our formula for the total differential, we get that df is the partial of f with respect to x, which is cosine x times cosine y times dx, plus the partial of f with respect to y, which is negative sine x sine y times dy, which we can rewrite slightly as df equals the cosine of x times the cosine of y dx minus the sine of x times the sine of y dy. Now to define an exact equation. Consider a first-order ordinary differential equation in differential form. So m of xy dx plus n of xy dy equals 0. If there exists a function f of xy such that the total differential of f df equals the same m of xy dx plus n of x dy from our differential equation, then we say that the differential equation is exact. In the next video, I'll show you an example where we verify that a given equation is exact.